Welcome back, everybody. We have an in-depth experiment to do today. I'm calling it the Ultimate Gold Sample Test. And we'll be answering some questions about testing ore samples with Aqua Regia. If you'd like to read through all this, you can. Just hit the pause button. But our main goals are to determine the presence or absence of gold in an ore sample using Aqua Regia, stannous chloride, and various samples of grind sizes and denoxing processes. Theoretically, they should all come out the same because they're all from the same ore sample. And although this process that we're using here is by standard qualitative to determine whether there is or is not gold, we're going to try and make it quantitative by doing some accurate measurements and some fancy calculations. Warning: the chemicals that we are using are hazardous. There is a risk of acid burns, lung damage, and death. Do not attempt these procedures if you are not familiar with hazardous chemical handling and proper lab safety procedures. Sounds like fun. Let's get started. Before starting, we need to prepare a fresh stannous chloride solution. Stannous chloride doesn't hang around very long. It has a short life. So we're going to fire some up here. To make stannous chloride, I just use hydrochloric acid and tin shot. So I'm going to mix about 50 milliliters of hydrochloric acid or muriatic acid with a couple of grams of tin shot and put it on the heater to heat. It'll dissolve into solution and we'll have our stannous chloride. Now, stannous chloride is very important during these procedures, although I don't show it being used much, but it tells you whether or not you have gold in the solution or whether or not you have precipitated all the gold out. And of course, safety procedures. We have to put on our gloves. Okay, I'm going to mix up some Aqua Regia for our test. This will just be our baseline test Aqua Regia. I'm going to mix 20 milliliters of hydrochloric acid with 0.5 milliliters of nitric acid. We will be using this to determine our density of our barren Aqua Regia. Later, we will be using this to compare with our pregnant solutions of Aqua Regia from our 4 samples of ore. For accurately measuring volumes, I have this 10 milliliter pycnometer. This will give us a very accurate volume measurement, which we then can compare with its weight to determine its density. We will take its empty weight so we can determine in the future the difference between its full weight and empty weight to calculate the mass of the liquid inside. Now we fill the pycnometer with water, and you'll notice when we put the top on, it'll squirt a little bit of water out through a hole in the top. That tells you that it's absolutely full and that you are now ready to take an accurate measurement. Being that water, or distilled water, is 1 gram per milliliter, this pycnometer should now weigh 10 milligrams. If it doesn't, then we have to do a small calculation to determine its calibration factor. This, in fact, weighed 10.375. So we'll use that in our calculations. Now, with our pycnometer calibrated, we can measure the density of our Aqua Regia. Now, this is barren Aqua Regia. There's nothing that has been dissolved into it yet. got a little too much in there. Okay, when we put the top on, it's going to squirt a little bit of acid out. That's why I need to be wearing gloves. There it is. Absolutely full. The volume of that should be 10.375 milliliters. And the density we'll calculate once we get the mass. Our measured mass is 12.06 grams. And entering that into our spreadsheet, we find that our Aqua Regia solution is 1.1624 grams per milliliter. That is our density of Baron Aqua Regia. Now to get started on the fun stuff. We've already randomly selected rocks. We've already crushed them to 1/4 or less. And we've already screened them into our 4 different sizes. We also have our 4 beakers of 150 grams dry weight of each material separated out. And now it's time to put 200 milliliters of hydrochloric acid into each sample. And here are the 4 samples. This is sample 1. We're going to put the hydrochloric acid in. And we're going to put hydrochloric acid into each one of these and preheat it just to give it a kickstart. Acids always work better when they're warm. You'll see me speeding through some of these sections just to condense the repetitive motions. If not, this video would probably be about 1.5 days long. Once everything was dosed up, we put it in the fume hood and on top of the heater to start cooking it. And had a problem.
A few moments later.
Okay, it really wasn't that bad, but this dish that I had the beakers in kind of exploded with a pretty good force. Scared the hell out of me. Fortunately, none of our experiment was damaged. So once we got things heated up, we need to add 5 milliliters of nitric acid to each beaker. So here we are, dosing our nitric into our test subjects. Now, as a rule, you want to add acids very slowly to whatever it is. You can get a runaway reaction, a lot of foam, your acids can boil out. In some cases, you might even have an explosion. So just add them slowly, take your time, there's no hurry. Alright, time to put them back into the cooking chamber or into our fume hood. But now that we don't have our big tray in there, we only have our small one. I can only fit 2 beakers in. So I'm going to have to cook these 2 outside, or should I say heat them, outside of the fume hood. Fortunately, we have good ventilation in our shed here. So we're giving everything a stir. That's part of the requirement of our experiment. So I brought out my small heater, and it's got a stir mechanism in it, which kind of makes it handy. 2 beakers are not going to safely fit on that surface, so I'm going to have to switch them off back and forth monitor their temperatures, and just make sure that we get things going in the right direction. Now, in that explosion, or the plate deflagration, whatever you want to call it, I did lose my stannous chloride. The beaker that it was in fell out and broke, so I have to fire up another batch. There's my hydrochloric acid, and we grab a couple of grams of tin shot, and we'll put those in the hydrochloric acid and put them back on to heat. That's about enough. That's good. Alright, there's our tin shot in our nitric or our hydrochloric acid to make our stannous chloride. We're going to monitor the temperatures on these beakers out here. Make sure that we get them up to an adequate temperature. Keep them about the same as the beakers in the fume hood. We need to keep this experiment all on an even keel. Each sample has to be treated the same way.
1 hour later.
And through the magic of video, our samples are ready. Sample 1, 2, 3, and 4. Different grind sizes. And they came out a little bit different color. I was kind of surprised. Number 1's a little bit more reddish. 2 is a kind of orange color. Number 3 is kind of orange. And 4 is a little red like number 1, but it's got some crud floating on the top. Probably just fine dirt from being such a powdered sample. And here's our fresh stannous chloride and our gold sample that we'll be using to test our stannous to make sure that it's good quality stuff. And you see we still have some tin fizzing away in there, so we'll set it aside and let it finish its thing. And here's our gold sample. It's still bubbling away some, so we'll let it go. Okay, next we have to filter each of these solutions. So we'll break out our vacuum flask. And we'll pour each solution through and filter it clean. Now this is a 100 micron filter, so it's going to pull out any of the stuff that we don't want in. Should give us a nice clean solution when we're done. Kind of looks like cherry Kool-Aid, but I don't think I would drink it. Okay, got a nice clear solution there. We're going to do this to all of the samples, all 4 of them. But we're not going to show them all, it would be too boring. Next we need to measure the density of each of the 4 beaker solutions. Again, we're going to go back to the pycnometer, fill it with solution, and weigh the mass. We performed this test on each of the samples and wrote down what the values were. We'll be calculating everything out in the end. And here are the filtered samples. 1, 2, 3, and 4. Next, we're going to take a sample of each of these beakers and put it into a test tube. That's 20 milliliters into each test tube. So here's the solution number 1 from the beaker. We're going to put a 20 milliliter sample into test tube number 1, marked 1U, because we're going to denox that one with urea. Then 20 milliliters of sample 1 goes into test tube marked 1S, which will be denoxed with sulfamic acid. And this continues on down through test tubes 2, 3, and 4. So in total we have 8 test tubes. And here are our test tubes ready to be tested. First we have to denox them. In the tubes marked U, they'll be getting 0.5 grams of urea. The tubes marked with an S will be getting 0.5 grams of sulfamic acid. So we're going to start off with denoxing with the urea. Now I've mixed a saturated solution of each of the urea and the sulfamic acid. So we're putting in 5 milliliters, which will probably give us about 5 grams. So we're pretty close. We're in the ballpark. And there's the sulfamic acid being added. Next we need to add some stannous chloride, which will tell us whether or not there is gold in the solution. So it's 0.5 milliliters of stannous chloride per test tube. If there was any gold in this ore sample, you'll see a purple color appear in the test tube. And there's a little purple coming up. It's getting darker. And you'll see as I progress through dosing these tubes that the previous tubes will turn purple and get darker as I move on. Well, so far our reaction is looking good. All the solutions are turning color. So let's let them sit a little bit and see what the final result is. Well, here's our results. Both of test tube sample 1 are a little bit lighter than the others. So I'm thinking maybe the coarse grind is not really giving us mineral liberation. And 3 and 4 look a little bit darker. So maybe the finer the grind, the more mineral liberation, the better retrieval you'll get. Well, now we got to place the leftover solutions that are left over from the previous steps into a single beaker and try and precipitate out any gold that's left over. And we don't want to go through all this work just to test a few test tubes. We want to get all the gold out that we can. So we're going to be using sulfamic acid to denox and sodium metabisulfite to precipitate out our gold. And depending on how much solution we have will determine how much sulfamic acid or denoxing agent, urea, whatever, and how much SMB you're going to use. Now it turns out that when I denoxed this solution, I did not denox it thoroughly enough, and I used a lot more SMB than I needed to, or that I should have, because the SMB will be trying to precipitate the gold, and the nitric acid will simply take it back into solution. So they have to fight it out. Eventually the SMB will win and the precipitate will fall. But you wind up using up a lot of SMB. Well, I got tired of stirring by hand, so I put it on my stirring plate, hot plate, whatever. And we mixed it for a while. Put in some more SMB. Now once it's properly denoxed and you put in SMB, the foam shouldn't happen, well, the foam will happen towards the bottom of the container, but once you have enough SMB in there, you'll get the foam happening at the top. It'll look like a head of beer. So you know when to stop putting in SMB when the foam happens at the top. Well, here's all of our solutions. We're going to let them sit overnight, separate out. We'll be back in the morning.
The next day.
Well, here's our test tubes the next day. Had some precipitation happening in there, some settling. You can see they're a bit clearer. It's theoretically the gold has settled out of the solution and should be at the bottom. I do see some black stuff down there. That should be our gold powder. Of course, gold in this fine of a grain is going to appear black. Let's take one of these outside and look at it. We have some sediment there. I don't know what it is, but we'll call it gold. We're going to go inside and take some of this solution and test it out. This is one of the test tube solutions. I'm going to check it and see if it has any gold. Put a couple of drops of stannous chloride in there. If there's gold there, it'll turn purple. And it's not turning anything right now. Let me give it a mix. Mix it up here some, see what we get. Yeah, it looks like it has a slight hue of purple, but mostly it's just gone clear. So all the gold has been precipitated out of that solution. Now we're going to take all the test tubes and pour them through this filter. Any gold that was in the test tubes has precipitated out as a solid now and will be caught in the filter. Just squeeze out every little bit we can get. Really wasn't much in there. But you'll see later as I pour in beaker or test tubes 3 and 4, there'll be a lot of changing of the color of the filter. That's 2. This is 3. Starting to see some color there. And 4. 4 looks like it might have the most in it. 3 and 4 look like they were the best. But to grind down to that level, to get number 4 down to a powder, gets very difficult to work with because all the powder wants to float away and plug up your machines. It's better to stay with the coarser grind. Well, here's our solution from all the beakers that was left over. We're going to run this through this vacuum flask here, through our Buchner funnel. If there's any gold in here, it would have been precipitated out and will stick in the filter. There's the big filter with the little filter laying on top of it. You can see how dark they are. And we're going to take these and stuff them into this piece of lead here. Made a little cup of lead. We'll stuff them in there, put them in this cupel, and cupellate them tomorrow. and see what kind of gold we get out. So that's it. Our experiment's done. What did we learn? Let's do some calculations here.
A lot of boring math later.
So we calculated the density of our barren aqua regia. We measured out our samples. And we've calculated the density of our pregnant solutions. And we've actually extrapolated the estimated ounces per ton, which those numbers are bullshit. There's not 11 ounces per ton or 13 ounces per ton in those samples. No way. So, anyhow, so our value calculations are not feasible with this method. Grind size between 1/8 and 200 mesh produce better results. Denoxing with sulfamic acid or urea produce comparable results. So these are the findings that I've gotten from this experiment. Your opinions may vary, but does it even matter? Well, thanks for hanging around. Hope you enjoyed the ride. I'd like to take a moment to thank my subscribers, my Patreons, for helping out with the financial needs. Thank you, honey. It's my wife. See ya.